All right, let's get started. So Ricardo is not here this morning, so he's not going to stop me. When it's time, you have to stop me. You might just go on and on and on and on. All right? Okay. So, all right. Now, I just want to remind you of something that we did yesterday. So we looked at the wave equation, how to discretize it, and so we looked at this very simple, intuitive scheme, this leapfrog scheme. This is very nice. It's a direct discretization of this partial differential equation. Okay? Now, and it's second order accurate. If you want to make this more accurate, if you want to go to higher order, include more grid points in this calculation here, in this stencil, things are very complicated and it's very difficult to derive a stable scheme. Okay? And so therefore, usually, for example, if you have taken a class in some numerical analysis, numerical methods for PDEs, quite possibly you have learned a number of schemes like Lax-Vendroff and things like that, which are different discretizations of in space and time. Okay? In practice, I think nowadays they are almost never used. Because it's very difficult to go to higher order in some systematic way. So what is used is some very simple method for which I will present some general results on stability. It's very easy to analyze, it's very easy to code, it's very easy to generalize to higher orders. It will not be the optimally efficient method, but finding the optimally efficient method for some particular equation for some high order is very difficult, and people will not spend this effort. So this method is called the method of lines. So if you want to solve partial differential equations, in particular evolution equations, do yourself a favor, use the method of lines. And so the idea is that you simply convert partial differential equations to a large set of coupled ordinary differential equations, and you do this by discretizing space and time separately. Let's say we have this simple equation, the advection equation with velocity is 1. And so what we could do now as a first step is we take the time derivative as it is without any change, but then we discretize the space derivative like this. So I is now the index of the grid point. So this is the second order accurate finite difference formula. And so now we have for the solution U at every grid point, we have such an ordinary differential equation. And it couples, because here we have U of I plus 1 and I minus 1. So the time derivative at each grid point is coupled to its left neighbor, right neighbor. If you do it more accurately, we have more grid points, higher order, then it's going to couple it to more neighbors. Okay, then we have more terms in this equation. So just doing like this, we have converted our PDE to a system of ordinary differential equations. We know how to solve ordinary differential equations, off we go. All right? There's one, however, now there's a subtlety. Okay? The subtlety, of course, is that if you make your delta x smaller, you have more grid points, and in the limit, you have infinitely many grid points. So the continuum solution corresponds to an infinite set of ordinary differential equations. And so if you take this limit, maybe things will not converge. Maybe because you take more and more iterations, maybe things are going to blow up. Okay? So now we have to find some method to ensure that that's not going to happen, that everything is fine. And the nice thing is that for well-posed hyperbolic differential equations, there are a very general theorem which says if you do this and this and this is all going to work out fine. Okay? And you're set. And so that's these results I will present now. All right. So now you have ODEs, and so in principle you can integrate these ODEs with any stable integrator for ODEs. So Sammarunga-Kutta method, for example. So if your method is explicit, so you have an explicit formula for the next time step in terms of the previous time steps, then usually there will be some condition on the time step, essentially this condition that we had yesterday, this current Friedrich-Levy condition, that makes the time step, you cannot take your time step too large. So the analysis, in fact, will show that you remember that the simplest Runge-Kutta methods would be Euler and Runge-Kutta 2, and they're not in this list because there's no way, even if you choose your time step very, very small, they will not be stable. So if you use Runge-Kutta, you have to use at least third order accurate, otherwise this is never going to work. Okay. All right, if it's implicit, then at each grid point you have to solve a further equation. You don't have an explicit formula, you have to solve a further equation. And then usually there are no or not very restrictive conditions on this time step for stability. But of course, for accuracy, you might be forced to choose a very small time step. And so, because of this very modular scheme, you choose some discretization, you combine it with some integrator. This is very, very flexible. It's very easy to plug in different time integrators, different space discretizations, different boundary conditions. It's very flexible, it's very robust, and these are key virtues in scientific computing. If you want to write a code that is able to solve different scientific problems, when you start a problem, you don't exactly know what will be required. Well, accuracy will be required. We want to be very flexible. So this is a very, very good method for these purposes. All right. And so the very nice result, we will have a little bit more detail, but it's basically that first order constant coefficient hyperbolic systems are stable with centered finite differencing and very simple restrictions on the time step, which you can compute explicitly. All right. Now, of course, okay, that's very nice. But usually I'm not interested in constant coefficient, and I wanted nonlinear. So this is for this constant coefficient linear, and I also want nonlinear. And then there's a simple trick that we'll talk about, adding some extra term, and then this is usually sufficient for nonlinear. So the whole scheme is really very simple. All right. Now a long slide to basically spell out the logic and spell out the result. So what's the result? So numerical stability for first order hyperbolic systems. Some of the things we have already written down in this very laborious lecture yesterday. So now this is my differential equation, first order in time. So now U is some vector or matrix, whatever complicated object I want it to be. And then P stands for the principal part. So the highest derivatives, which is in this case just all your space derivatives. And so this is some expression in all the space derivatives that you have. All right, then we have already worked yesterday with the Fourier transformation, so you can Fourier transform this, and then derivatives are replaced by multiplication with the frequency. Sometimes we write omega, sometimes we write omega as xi divided by h, depending on what's more convenient. And then this function by Fourier transformation becomes a p hat in the Fourier space, which now depends on omega or I omega. All right, like this, for example, for the derivative with some coefficients a. And now we remember, so well-positiveness was equivalent to restricting the norm and making sure that the norm doesn't grow faster than some fixed exponential. And so we've discussed this yesterday in terms of diagonalizability of the principal part. Yesterday we called this A. Now we use more standard language for this kind of work. We call it now P of delta x, but it's the same thing. So we now this principal part in Fourier space needs to be diagonalizable. And this is a simple linear algebra check that we can do. Is this matrix diagonalizable or not? But this is the continuum problem. Now we have to go to the discrete case. So now we discretize this, whatever. For example, second order centered finite differencing. Let's take it easy at first. And then you have to Fourier transform your derivatives to the discrete. So first you have to discretize it and then do the discrete derivative in Fourier space. And so we had this also yesterday. Remember that we discussed that there was this, well, wrote it as the sine omega h divided by h. So if h is small, this is just this. But then if h is larger, then then this is a it's not the continuum result, but you have some numerical error. You can just try to derive it as an exercise. So this is the space discretization in Fourier space. Now we add our time integrator, let's say nth order Runge-Kutta. So now we write our time update, so the solution V, the discrete solution V at time step n plus 1. It's some operator, some matrix, which operates on the solution V at time step n. It turns out for Runge-Kutta methods, it takes a very simple form, which is very convenient to analyze. So this principal part term, which goes into the Q, this is just a polynomial function. So this makes it very, very easy to analyze it in practice. You can also analyze for non-Runge-Kutta methods, but algebraically this is much, much simpler. Now, if you write, this is Fourier space, which is basically the same. This is the same relation as before, except that the V now has a hat, and Q has a hat, because now everything is in Fourier space. And so this is the relation for going from n to n plus 1. Okay? But now we want after n time steps, so we want to say what's happening at the nth time step, so starting with time step 0. So this update operator Q in Fourier space Q hat, you have to apply it in time, Q to the n, applying this matrix n times. So this Q, we also call this the amplification matrix, because it tells us whether this solution grows or whether it decreases. If it increases, then in general this is unstable. And so now you can check that if the P, the principal part, is diagonalizable, then this is also diagonalizable. So this feature carries over. And so if it's diagonal, then we can discuss its norm simply in terms of all of its eigenvalues. And then it turns out that the condition that we need simply is that all the eigenvalues have to be smaller or equal than 1. Better strictly smaller than 1 if you want to be on the safe side. So now we have reduced basically the spatial discretization part of the whole problem to simply studying all the eigenvalues of this matrix and just checking whether they are bounded by 1, which is relatively straightforward. Well, if you have the whole Einstein equation, maybe it's a little bit longer calculation, but in principle it's entirely straightforward. And then the only thing that comes in addition is if you have an explicit time stepper, then you need a restriction on the time step. Okay? Just like this current Friedrich-Levy condition. And it turns out if your partial differential equation does not explicitly depend on the direction or which dimension it is, which usually the kind of equations that we have, they don't do that, then this current factor, we here lambda delta t by delta x, it satisfies an extremely simple relation. It's just a ratio of some, what here is called alpha 0, which is some number which simply depends on your integrator. So for each integrator, you can calculate this. So this is ICN. It's called iterative Krankel-Nicolson. It was extremely popular for a decade or so in numerical relativity. Don't use this. So they don't even have to know what that is. Runge-Kutta 3 has square root of 3. Runge-Kutta 4 has square root of 8. You see, if the time step limit is larger, for Runge-Kutta 4 is better because you can make larger steps and it's computationally cheaper. So you compute this number, and then this is divided by sigma of A. Sigma of A is the spectral radius. I should have written P. Sorry, just jumping around between different conventions. This is the spectral radius of your principal part matrix, so basically the largest eigenvalue. And then you have to divide it by the square root of the dimension. So that's very interesting because, for example, if you do the wave equation in one spatial dimension, you have a certain limit. You can try this out, whether this is really true, whether this formula gives you the correct answer in one spatial dimension. But if you go to higher dimensions, let's say 3 spatial dimensions, you have to take a smaller time step, in fact, by a factor of 1 divided by square root of 3. Okay, so which makes everything more expensive. Going through 3 dimensions already makes it more expensive, and then your time step also has to be smaller. But it's a really simple formula. This is one of these advantages of using the method of lines, that once you have your equation, you have a certain associated linear algebra problem, you compute some eigenvalues, you know what's the number that comes with your integrator, and you have your time step. Very, very simple. Okay. Now, so this theory applies to constant, coefficient, and linear, which is usually not what you're really interested in. So you want nonlinear systems. And so for nonlinear systems, you have to add one more element, which is numerical dissipation. Okay? Now, I don't think I say anything about... No, I say it's hit here. Let's stick to the end. Then I make this comment. So, if you have quasi-linear but non-linear hyperbolic partial differential equations, you can use just the same numerical methods. You just have to add one element with this numerical dissipation, which basically dissipates high frequency modes. If you have a linear equation, this equation acts separately on all of the frequencies, all the modes that you have in your problem. But if the equation is nonlinear, then these frequencies, they mix together, they couple together. And what's usually happening is that there's some transfer of energy, some frequencies to some other frequencies, and usually there's a transfer of energy to the high frequencies. Does it mean that there's a transfer of energy to the high frequencies? This means that if your initial data look like this, very nice and smooth, you evolve this after some time, you get some high frequencies, it gets very noisy. Okay, and then it's not well resolved, and it gets even noisier, and your problem becomes unstable. So what we have to do is to ensure that this doesn't happen. Okay? Usually, in fact, for first order methods, if we analyze these amplification factors as a function of frequency, what we usually get, so Q as a function of this variable xi, which goes, so the absolute value of xi goes up to pi. This is the maximum frequency in the grid. The way what this would look like is that at zero frequency, this would be 1, but this is okay. So at zero frequency, this can be 1, exactly the limit. There's no problem. And then it decreases. So the higher frequencies, they are damped, as they should be. But then the mid frequency, pi over 2, there's a minimum, and then it goes up again, and the highest frequency is not damped. And that will make it unstable. This will create some coupling between the modes that become unstable when you have nonlinear couplings. And what you basically have to achieve is that this damping factor is smaller here. So you want to just, this eigenvalues Q, these damping factors, you want to make them smaller. You would like to make them, I don't know, instead of this, like this maybe. Okay? That's what you want to achieve. And the way you do this is by adding a term to your evolution equation like this, just adding by hand some term. Now this is modifying your equations. Now you have a different equation that you want to solve. So what's the way to make it consistent? You have to make this converge away in the limit that your grid spacing goes to 0. All right? Fine. So just we just multiply this by something which just converges away. And in general, what you add is a term of this form. It looks kind of complicated, all right? But the basic idea, what you do, where's my? Here. The basic idea is you have your equation, whatever dtu is equal to whatever your right-hand side function is, okay? And then you add this term. And if you're at lowest order, what this corresponds to is basically just you add Laplace or second derivative of u, and then you make it converge away, multiply that with the grid spacing. Okay, and why you add Laplace? Because what is this equation? If I don't have this, what's this equation? It's the heat equation. It's a parabolic equation. Or what is the heat equation doing? If you have some initial, right, you know this, if you have some initial profile, my initial profile looks like this, and then I evolve this with the heat equation, then the profile decays. and the heat goes away. Okay, this is what parabolic equations do. So adding this term, it will just, if I have some wiggle, it will just decay away. All right? So this takes out the noise from my equation, but I do it in such a way that in the limit this term vanishes. Because in the limit of infinite resolution, I need to apply less and less dissipation. All right? But then this is basically first order accurate. So if I want to have higher order schemes, well, basically what I'd have to do is I have to generalize this a little bit. And the standard way of generalizing this is with this particular expression, but basically this is a first order derivative, is another first order derivative. You have to take this to some power, and then you have to scale it appropriately. And so the problem with now there's a little catch. There's a sigma here, which is some parameter, which is basically the amplitude you add. And that's up to you, okay? That you have to choose. So if you add too much dissipation, so if you add too little dissipation, then it's still going to be unstable. If you add too much dissipation, it turns out it will decrease your time step limit. Why? Because it makes your equations behave more and more like the equation, and the heat equation has a much smaller time step limit, and so it doesn't work. It'll become unstable. So now you have to choose, like, what's a good value, okay? And if an evolution is very, very expensive, it may not be very convenient to you really find a good value. Then you may rely on what other people have chosen. You make some experiments. Then it becomes very tedious. Then it becomes a bit of black magic of what's the experience, like art, okay? An art of tuning the right things. But there's this very nice and solid theory behind it. Unfortunately, there's a free parameter. Now this parameter you have to find by yourself. All right. Now, when you talk about dissipation, one has to mention some other thing that what I mentioned yesterday is that, for example, when we have wave equations, the solutions are smooth, but when they are fluids, they can become distributional. Now, if you have something which is so sharp, like a distribution, adding dissipation is very dangerous because it may change the physical behavior of your solution. It may look completely different. So then you may not. You could use this, adding additional artificial dissipation, but it may change your solution, make it unphysical. So in that case, you probably want to do things differently and use entirely different methods. And probably Luis next week is going to talk about this. Okay, so for example, if you read something about dissipation, people say, oh, dissipation is very, very bad. Probably they talk about it in the context of fluid dynamics, which behaves completely differently, and you simply have to use different methods. But if you do something like you're wolfing black holes, dissipation is your friend. Okay. Now, I have some slides about second order systems, which I want to go through this very, very, very quickly. Because, so if you have already seen the ADM equations, they're actually second order in space. By introducing the extrinsic curvature, you have first order derivative in the metric, first order in the metric, so in the extrinsic curvature, so it's first order in time, second order in space. So this is not a first order, it's not a first order symmetric, first order hyperbolic system, and all this theory doesn't apply. But it's very nice we have already seen for the wave equation, if you take the wave equation, we make it completely first order, you get lots of extra equations. They may become unstable. Maybe you want things in a more compact way. Maybe we want to keep a formulation which is first order in time, second order in space. But it's not covered by the theory which we have so far. Okay? And so mostly, it's driven by the needs of numerical relativity. The mathematical theory for how to treat first order in time, second order in space systems, this has been developed in the first years of the 2000s, and now there's a theory for that, which somewhat extends a little bit the theory for first order systems, and you have the same rules, but you have to treat it slightly differently. And so I'll just flash basically the main results and what this looks like, just to give you a feeling, just to make you aware that this exists. And then I want to show you some plots at the end. So, all right, so this was done quite late. Let's just proceed. This is the motivation. Let's just proceed. Right. No, I want to say something very specific about this. So this was quite confusing for people. So if you reduce something to first order in time, you can say, well, reducing first order in time, reducing first order in space. It looks kind of the same thing, but it's not. So if you reduce the first order in time, you get new evolution equations, and that's completely fine. It doesn't really change the well-posedness properties at all of your equations. But if you reduce the first order in space, you have new evolution equations and new constraint equations. So this makes your solution space a little larger, which means it gives new unphysical degrees of freedom, and these may give rise to new instabilities, which you have to treat. And in very complicated spacetimes with black holes, that may not be convenient. And so this is the motivation for second order in space. Now, for example, you can do this for the wave equation. So now you can say we keep it in this form. So first order in time, second order in space, but just introducing a new variable. Which basically, before we called that pi, now I call it k to emphasize the analogy with the ADM equations and the extrinsic curvature k in the ADM equations, because this is this kind of variable. And then I can go to the frequency domain. That was quite useful up to now. And then what you can do is in the frequency domain now you introduce a new extra variable, which makes it look more like a first order system. Then you analyze this first order system in Fourier space just like you did before, and then you find the same results as before. But now because you have introduced an extra variable, when you check your well-posedness, which usually the norm that you have to use is like the L2 norm, now in your L2 norm you have to include the norm of the extra variable. And since the extra variable did correspond to the space derivative, you have in the norm this extra term, which is an entirely kind of trivial observation. It just confused relativity people and numerical analysis people for about a decade. And then you can just treat it. Then you can just treat that like before. So in principle, this simple analysis of the wave equation shows there's nothing bad with doing second order in space. It works fine. But now, if you want to, for example, analyze the ADM equations, which are very complicated, then you don't want to do this like on a case-by-case basis. What you would like to have again is some simple rule of this is what you have to do. This is the matrix that you have to analyze. Just a recipe that you have to follow. And such a recipe exists. It's slightly more complicated than the first order in space form. And basically, you have to. You're right. So it's first order in time, and now you have to all the variables that you have in your system. Many variables. You have to split them into two parts. Basically, those that have second space derivatives and those which not. And then so you split the variables into two parts, which means that the principal part you split into four components, because now it's like a 2x2 matrix, and it has this kind of funky structure where you have to identify all these different parts. And then there's accordingly definition of your second order principal symbol. And then you can basically do the same analysis before, but now it's not just the analysis of this one matrix A, but you somehow have to take care of these different matrices which appear in this kind of normal form for second order systems, which is a bit more complicated. And then you essentially do the same thing as before, until you hit a problem, because now in the continuum problem you say, okay, I just have to add this term to the norm, the derivative, but in the discrete problem you don't know how you have to discretize it, and then it turns out you can just make a simple choice. So then you essentially have basically the same things as before, except that so at one step there's a thing where discrete stability is not implied by well-posedness plus centered finite differencing plus small delta t. So there's some recipe, there's some normal form, but and for the continuum problem for well-posedness, this is completely as before, but if you want to really go to the discrete problem, you have to work out certain things on a case-by-case basis. So it's slightly more complicated. But then I wanted to conclude with this kind of picture, which is useful to have seen once. So now you have your numerical scheme and you have all these definitions. And now you can compute of your waves in the discrete scheme, you can compute your phase velocity and your group velocity. So basically how fast information propagates in your numerical scheme. Okay? And so let's apply this, for example, to the advection equation and the wave equation, let's say second order and fourth order. Let's just look at one of the plots. Let's look at group speed, which is kind of a more relevant thing. Okay? So this is for the wave equation, advection equation. So the proper continuum propagation speed is 1. And so we see that so this is 0 frequency. So when the frequency of the wave is very small, then your waves are propagating with the correct physical speed of 1. So that's nice. But then if the frequency increases, so if your wave gets less and less well resolved, your numerical errors are larger, and so the wave doesn't propagate with the correct speed, but with a smaller speed. Okay? This is called dispersion error. And so you see, for example, so this is fourth order, this is second order. So fourth order is better because the speed is higher, it's closer to the correct value of 1. If you would go to, let's say, sixth order, it would be even better. Okay? And it also basically tells you if you have some component in your grid which has like this frequency, what is the speed at which this frequency travels through your grid. All right? And then you see something else. So the wave equation, if you discretize it second order in space, you see that the velocity always is the same sign. It's always positive. And for the maximum frequency, it's 0, but it doesn't get negative. But for the advection equation, which is taken here as an example of a first order in space system, you see that at some point it actually crosses over and the velocity becomes negative. Okay, so your modes, they go in the wrong direction. So this is particularly worrisome if you have a black hole, because in the continuum problem, all the information falls into the black hole. But now, in this discretization, some modes go in the wrong way, so instead of falling into the black hole, they're actually coming out of it, which is certainly not very desirable. Okay? And what you would have to do is then you have to use this artificial dissipation to make sure that all these unphysical modes are sufficiently quickly damped out so that they don't contribute to your solution. Okay? So that maybe your amplification factors more look like, I don't know, let's say this. That all the high frequency content is damped out because the high frequency content actually travels with the wrong speed, the sign is wrong. Okay? So these are things that you have to be aware of when you apply these schemes to things like black holes. And I think that's all that was left over from yesterday. And so now, how are we doing with the time? All right, I'll have some more time which has to go to tomorrow. So now all this hard work of numerics, now we want to apply it to some physics. And let's start with black holes. There will be one lecture of black holes today. What are black holes, how we set up initial data, these kind of things, a little bit about the physics of black holes, and then tomorrow we'll talk about evolving them. And so this lecture, I would have wished, in general, you can always do better lectures, but this one in particular, I would have wished I have a much, much better lecture than what I've prepared, because one of the most important people to contribute this is an Argentinian, Sascha, that he died quite young, not long ago. And so I want to dedicate this to him, which is a very incomplete thing because it's maybe not such a great lecture, but I think it's good for students maybe from South America. That one of the key people that have contributed this is somebody from Cordoba. Now, first, what are black holes and what are event horizons? What do we have to know about them when we do numerical relativity? So now, I think you're all familiar with Penrose diagrams. Here, a nice simple Penrose diagram of Schwarzschild. I think you're this in Luke's lectures. You have seen some Penrose diagrams. Yes? Who doesn't know what kind of diagram this is? Now is the time to speak up. Penrose diagram? No. You had to speak up. You had to speak up. Did Luke show? I thought I saw in his slides he had some Penrose diagrams. No? All right. So these are very, very useful diagrams. I'll just explain this. Take some extra time. Okay? In order to understand what's going on in the space-time, you want to make a picture. You have seen these nice pictures and movies that Rodrigo had yesterday, of his event horizon and the Eddington-Finkelstein coordinates. Interesting things were going on, and so I think the details were interesting. But one of the things I think you can learn from that was that in order to understand the physics of some thing that is going on in the space-time, different pictures emphasize different physical content. Different coordinate systems emphasize different interesting things which are going on. Now, one particularly interesting type of coordinate system is when you say, okay, let's just choose coordinates such that my light cone goes at 45 degrees. Okay, because so the light cone is important to tell you about what's the causality, which points are causally connected and which ones are not. So this goes via the light cone. And so having the light cone simple, like going at 45 degrees, that seems like a good idea. Okay, so let's do that. Let's choose these kind of coordinates. But then another thing that's important for causality is, for example, we talk about black holes. What is a black hole? So a black hole is something where you can't get out, you can't escape. All right? So even if you wait until infinity, you're not going to get out. So somehow you have to include like the whole space-time until the complete future. Also, if you want to calculate the gravitational waves or electromagnetic waves which get out, you have to compute what are these. You have this binary black hole merger, which is something which happens within maybe 200 kilometers, and you have to compute what happens 9 billion light years away, which is practically at infinity. So you want to be able to do calculations like at infinity. All right? And so now what you do in addition to this, that you choose coordinates, you reparameterize, so that still your light cones are at 45 degrees, but you pull infinity in like a finite region. Okay? Like infinity is like x equal 1. Okay? And so you can do this, and if you do this, you get this kind of diagram, which is called a Penrose diagram, or Penrose Carter diagram. So here, light cone was at 45 degrees, and this is the outer boundary here, which is infinity. That's like different points. So for example, if you have a space-like curve, like t equals constant, maybe, so this goes to space-like infinity, which is called I0. But if you take a light ray, let's say here is that a light ray, we go all the way to infinity, you end up here, which is called null infinity, a light-like up. This is also called scribe plus, script I. All right, and then there's an I plus, which is future time like infinity, and I minus, which is future, past time like infinity, and so on. And then these lines, this is the event horizon. So what in this picture is actually the event horizon? So now you can see. So these are all the points at infinity. These are all the points where you can send a signal to the future. All right. But now if you go. Now we have the same problem as yesterday. That you see that if you go back from this point now, there's this region out. Okay? So if you're here, you can send a signal to infinity. You can send a signal to LIGO or to some telescope, but not if you're here. So what we do, we call this the black hole region, and is the horizon, the event horizon. Okay? So having this kind of causal diagrams which show you the whole history of the space-time, you can very easily understand what's the causal behavior, and you can very easily define what is a black hole, which is basically you go all the way to the future, and then you trace back a light ray, and the parts which can't reach here, the black hole. All right? Now the funny thing is that there's there are 4 parts to this. There's this, and this. Now, probably we will actually need this tomorrow. Are you familiar with what is an Einstein-Rosen bridge, like this kind of wormhole picture of Schwarzschild? Have you seen that? Who hasn't seen that? Everybody has seen it? You've seen it? Yes. All right. Yeah, we have seen this all. Okay. Right. Excellent. So what this, we're going to use this several times, right? What this means is, so if you're far away, for example, if far out, this is a sphere of r has some value, r equals constant. So if you're far out here, 1 point, one point is a sphere of a certain large radius. And now if along a slice I walk in, then these spheres become smaller. But then like here, there's a smallest sphere, which we call the minimal surface. And then if I go further in, they become larger again. Okay? So like that, there's another infinity inside. All right? It's like you know the witches. The witches, they have these crystal balls. Right? And so if you look at the crystal ball, there's like a whole world inside. Okay? You can think of this, the minimal surface. It's like you have 3D. This is like a crystal ball. It's like there's a whole other world, wormhole. All right? Except in this case, you see, if you want to go from one side of the wormhole to the other one, it's a space-like curve. So you can't make this a causal curve. You cannot cross there. It has this spatial topology, but you cannot fly from here. You cannot fly from here across through. All right? All right. So that's what I wanted to say about this picture. And so now we have some numerical spacetime. So now how do we find the event horizon? We basically find the event horizon. So the first thing is, I'm not sure now if I say this actually somewhere. Yeah. So applying the rigorous definition in a numerical spacetime doesn't work, because the definition is basically go all the way to infinity and then take a light ray back. But we don't have infinite computational resources. You will have to evolve till infinity. Okay? So our evolution maybe ends here, but maybe late enough. Okay? And so then we take late enough, and then we just follow light rays all the way back. Okay? That's the basic idea. If you have what we saw in Rodrigo's thing yesterday, if you have a light ray here, it's going to go out. If you have a light ray here, it's going to fall inside. So now what I can do, for example, I can take several spheres of light rays, trace them to the past, and so the ones that are inside, they will be attracted to the horizon, and the ones that are outside, they're also attracted to the horizon. Now you say, well, you don't see this here because light rays are at 45 degrees, and they're all parallel to the horizon. What I'm talking about. But so this diagram has coordinates which are to causality, but not, for example, the physical distance. So the distances are wrong. So a light ray which is here completely in parallel, here will have a huge distance from the horizon, and here is going to have a very small one. Okay? So if you would make it in kind of this picture, a different picture where the x coordinates are now something like distance, and you take a light ray here, it would get attracted to the horizon, and one here also. And so what you basically do is you start in the future, at the end of your evolution, and then you trace your light rays back in time. You can do it with individual light rays, but what's actually better is you do it with a whole surface. And so what you do is, as a general method, it's quite useful, is called the level set method. So what is it? Let's say we have some function of x and t, and we define the event horizon by f is 0. Okay? Now, if this surface is 0, it's that this is a light-like surface, then basically the gradient of this is a null vector. So this, with the metric, is 0. Now I can just write it out explicitly, and I can write it as an evolution equation for my function f. This t should go up, sorry. Okay, it looks a bit awkward because there's a square root and so on, but this just gives me an evolution equation for f. Now I evolve this backward in time, and then this level F equals 0 will be attracted to the event horizon. That will find where's the event horizon. Okay? And then you can get pictures like this, for example. This is a picture of the event horizon for some unequal mass black holes as it evolves, how they go around each other, and then they merge, and you see the ring down that Janis mentioned yesterday. And at the end, you have basically a stationary solution left over. Nothing's happening here. And the way this is constructed, you go all the way to the end, and then you evolve this equation backward in time, and you get this picture. Okay? Now we know, if you have a numerical space-time, we know how to find the event horizon. And in fact, there's lots of interesting geometry and mathematics associated with these event horizons, but I won't have time to go into that. All right. Now, for many practical purposes, so event horizons are very nice, are the true definition of a black hole. But since you're doing like backwards in time, they have a number of features which make them hard to handle, and we want to deal with another concept which is more convenient often, which is the apparent horizon, which is something which is local in time. Now, the word apparent, you might get fooled because it's only apparent, but it has some coordinate dependence. Now, everybody knows who doesn't know what is an apparent horizon? Apparent horizon trapped surface, we all know what that is or not? Everybody knows it. I can ask you questions and you know it. No. All right. Say it. So the idea is the following. Well, what's a trapped surface? It's a space-like two surface with the property that the ingoing and outgoing wavefronts decrease in area. So light cones tip over. Like this is a space-time diagram, maybe not a very good one. Black on black. It's hard to see. But time goes up, space goes this way. This is the event horizon, and so now you have light cones. They kind of, under the force of gravity, they like tip over, and when they have completely tipped over, all the information is flowing inside. All right. So this is the apparent horizon. There's another. I have to think about how to draw it in the right way. So let's make another drawing. This is this wonderful. So here my space-time diagram. So this here is a two surface. Okay, I've suppressed one dimension. A two surface at a given time. Imagine. On this two surface, you have a lot of light bulbs, and you flash your light bulbs all at the same time. Okay? What's going to happen? You will have a wavefront of light which is going out, and you have another wavefront of light which is going in. Okay? In Minkowski space, what's going to happen to the area of this wavefront? While the one that's going out, it will expand, and the one that's going in, it will shrink, obviously. All right? But now, if you have very strong gravity, so now you turn up gravity, you can imagine that these ones, like they go in faster, but maybe these ones, under the force of gravity, are curved. Now, maybe they go more like that. Okay? Now you make your gravity stronger and stronger. If you have a black hole, gravity is so strong that the light can't escape anymore, and so your light rays somehow they turn back, they fall back inside. Okay, and you can describe this by whether the area of this wavefront becomes larger or smaller. And if the wavefront area becomes smaller, then you call it a trapped surface. The surface can't get out. Okay. If you're just at the limit, it doesn't get larger, it doesn't get smaller, it stays constant. You call it a marginally. You call it a marginally trapped surface. It's just going straight up. And the outermost one, the one that's closest to infinity, you call this the apparent horizon. Okay? So this is some surface where at the boundary of this surface, basically all of the light cones are looking inside. All of the information locally is flowing inside. All right? So this is something which we can find at any time. We can find whether we have such a surface. We don't have to wait until the end of the evolution like with the event horizon. We can check this at any time. And we can actually write down a nice equation, which is this one. Theta is the expansion. So basically theta is the time derivative of the area. So if theta is positive, the area becomes larger. If theta is negative, the area becomes smaller. And we have plus minus because this is the outgoing and the incoming. Okay? So the horizon is just the boundary. So this is where this is 0. And so now we have to solve that this equation is 0. R is the unit normal, outgoing unit normal of this surface, this vector R. And so in terms of this vector R, we have this case, the extrinsic curvature, trace of the extrinsic curvature, and this is the divergence of the unit vector. You remember what the round D is? What's the round D? You remember what that was? The covariant derivative in the spatial hypersurface, exactly. All right? So this looks quite compact. Of course, if you write it out, it comes a bit messy, but it's something which you can solve directly with an elliptic solver or other methods. In fact, the one to use is this one. And if with all the gory details and more the gory details, there's a very nice living review about this, and there's this paper from 2000, which is very long and has all the details you ever wanted to know, how to find these things. Here I have a few more details. Let's see what I have. So this is the wonderful equation. If you see time symmetry, if the extrinsic curvature is 0, becomes even simpler. It says that the divergence of this vector is 0, so it doesn't grow in area, it doesn't shrink. And this is exactly the simple, this is exactly the situation we have here with our wonderful, let's give it a standard name, right? Einstein-Rosen bridge, the embedding diagram of Schwarzschild spacetime, and what I wanted to say. Yeah, right. So this is the minimal surface here. So this is the surface which is just one way expands and the other way also expands. So that's has a simple interpretation. And basically what happens if you add the other terms, it looks kind of similar, just going to shift it around a little bit. Maybe it looks like this. No, this is going to be bad drawing. Whatever. It's like tilted a bit, okay? Something like that. And then there's lots of interesting questions to have. Lots of people are working on all kinds of mathematical theorems related to these things, but unfortunately, there is no time to talk about this. But if you want to know more, you can talk to the guys from Cordoba. You have lots of people working on this, all these interesting questions. All right. So now, how we solve this equation? Well, same technique that we had for the event horizon. By a level set surface, you say my surface is described by f of x equals 0. And then I can rewrite this in some, now not so nice nonlinear function derivatives of the level set. And so if you have just spherical symmetry, basically it's just zero finding. It's very simple. In axial symmetry, it's an ODE. You see it's a nonlinear ODE. It's a bit awkward, but you can solve this with standard ODE methods. And in fact, I haven't put it yet, but I'm going to put, if somebody's interested, I'm going to put some 2 or 3 pages of precise descriptions of deriving this and how to solve it. I'm going to put it on the website. And then in 3D, which is more interesting in what you do in 3D, you use what is called a flow method, which is very nice. So basically, the idea of a flow method is, what is it? This is my actual apparent horizon. That's what I want to find, this surface. So what I do, I start with one which is much bigger, bigger than this one. All right? And so now I write down some equation where if I make this now contract this in radius, it will get stuck here. Okay? So it will be attracted to the correct answer. So for example, one way of doing this is this one. It's called expansion flow. So lambda is basically some unphysical parameter, a parameter in this direction, and my equation, so it's the lambda is 0 where I start, and now this is the unit normal, and so I just solve basically lambda, so x coordinate prime is expansion time is. So if you can see that on the correct answer, the expansion is 0, so this is going to stop. Okay, you could worry whether it really converges and so on. For a time symmetry, it does it, and usually this also works quite nicely if you don't have time symmetry. However, this is a parabolic equation. It has very severe time step restrictions. It's very, very slow. So in order to make it really work, you have to do all kinds of extra tricks to make it really fast. And you expand it in spherical harmonics. You use some extra tricks, but this works very well. There's an implementation, for example, the Einstein toolkit, which has a bug. But if you want to use it, you can ask me how to fix it. And this is a very nice, very robust method that is working in general. All right. So now we have. So if you have a numerical spectrum, we can find event horizons, we can find apparent horizons, and we can find out whether there's a black hole or not. Okay. But how do we set up our initial data to make sure that it has black holes in the first place? For example, say, okay, I want to set up an evolution for binary black holes. Now I have to find initial data for the Einstein equations, which has 2 black holes and not 1, 3. How do I do that? Okay. Now we have to first find out how we solve for the initial data, and then we have how to put in a specific number of black holes. We have already met the equations, so these are the constraint equations, which we have already seen. And now the first thing we have to do is we have to find out in these equations what are the quantities that we can choose freely, and what are the quantities which are determined by the equations. Because that's complicated, let's do Maxwell first. So you know Maxwell, these are the Maxwell constraints. How you actually solve those. And so a standard way of solving this is you choose freely these 2 3-vector fields, AE and AB, and 2 scalar fields, phi E and phi B. Then you solve these elliptic equations. Sorry, I'm stupid. you define these freely, and then you define those, and you solve these 2 equations, and then you construct the initial data as the gradient of these fields plus this extra term, which is free. And this gives you a result which satisfies this equation. So what is involved is some kind of splitting into types of different quantities. Certain things you can do freely, and for other ones you have some equations. All right? And so now we're going to do the same thing for the Einstein equations. I will do this in like 2 steps. So first, so for the Einstein equations, there is no unique way of doing this. There's several ways. This is somehow the one easy way, which is quite general, and the other way called conformal thin sandwich, other standard way, and takes many ideas from here. It looks a little bit similar. All right, so let's do simple. Let's do time symmetry. So extrinsic curvature is 0. Then the only equation that we have is the scalar curvature of the metric is 0. All right, but now the metric is a matrix with symmetric 3 by 3 matrix has 6 variables. We just have one equation for 6 variables. Isn't convenient? Okay, because we could make an ansatz, that this is basically, I don't know. So this is hxx, hxy, and so on. Okay, and we say we just leave one free. So we leave this one free and fix all the other ones. But why pick hxx? This is not very natural. Okay, so what works very nicely is the following. You fix some arbitrary metric h bar, which you call the base metric, and then you just multiply this with some factor. The power of 4 is chosen because it gives you the simplest equations. We call it a conformal factor because it leaves the angles invariant. You can do this as an exercise. Why rescaling a metric with a function with a scalar, why it leaves the angles invariant. And then you can compute how the scalar curvature transforms, so how the scalar curvature of this is related to this. This is quite a simple formula. And so now if you want that this one is 0, you just from here you read off this. And so this is an elliptic equation. The scalar curvature of this, which you can compute, and then there's a Laplace acting on psi as a linear elliptic equation. So this is a very nice and algorithmic way to tell you what you can choose freely, this, and then there's an equation for this, and together they form the metric. All right? And this is very nice. And if you don't have spherical, and you don't have time symmetry, if you have your extrinsic curvature, you do like almost the same. But clearly, the whole thing gets a bit longer. And so what you do is you take your extrinsic curvature. First, you remove the trace. You call this A. Then you have to do some rescalings again with a different power of psi. And why that power of psi? Let's worry about this. And then you make some decomposition, which is a little bit reminding of the one that we did for electromagnetism. And you write this as a TT part and something else. TT stands for transverse, or divergence free, and traceless. So it has 0 trace and 0 divergence. And then this other thing here, this vector potential, satisfies some ugly equation. I'm calling it beautiful equation here. And then you insert this whole slew of definitions into your constraint. You get these ugly equations, but again, they're nice coupled elliptic partial differential equations. There's an elliptic equation for W, and there's another one for psi. It's the same. This is the part we had before, and now it just adds some nonlinear terms to the problem. You can freely specify this, and this, and then you compute the W and the psi, and you have the whole data. So there's a nice algorithmic way which tells you what you can choose and what is then solved by the equations. All right. Fine. This is the general story, but now we want to have black holes. How we get black holes? Same story as always. Let's do simple first. Let's choose the simplest base metric. Was the simplest choice, flat. Okay? So this is called conformally flat. So now my 3 metric is a factor times the flat metric. What's a good example for a flat metric? Well, Minkowski, but also Schwarzschild. Schwarzschild is conformally flat. All right. Kerr is not conformally flat. The Kerr spacetime, a spinning black hole, cannot be written as the flat metric times a factor. But you can think of it as conformally flat plus some extra gravitational wave. Okay? That's sort of traveling around. So let's keep it simple. Let's first choose extrinsic curvature 0. So only the Hamiltonian constraint, the scalar equation, remains, and it is Laplace psi 0. Laplace psi 0, we all know how to solve this. The boundary condition is that infinity has to go to 1. So it's 1 plus a sum. Sorry, there's a line missing here, absolute value. It's simply a sum of terms 1 over r. Okay? Add as many terms as you like. Now you can try to discuss the geometry of this spatial geometry of the metric h, and you will find that so this is called Brill-Lindquist construction, Brill-Lindquist data, and it's basically this Einstein-Rosen bridge from Schwarzschild like several times. Okay, so with some deformation, but it's basically some extra copies of that. All right, so this will have several minimal surfaces, one here, and so on. This is also called puncture data. Why puncture? Because at some points, at these points, the whole thing blows up. And you can analyze that these points, they belong to another infinity. If you compute the physical distance between any point here and the point with these coordinates, you will find that physical distance is infinity. So these go all the way to infinity here. So these are kind of singular points. They're called punctures, like you make a hole in the space-time. These points there's a coordinate singularity, But you will have, basically with each of these minimal surfaces, you will have associate one of these apparent horizons. All right, so if we put in 2 of them, we get 2 of these wormholes, and we get 2 horizons. All right, so this is my recipe for constructing initial data with 2 black holes. All right. But now the problem is, so I want more general. I want my black holes moving around, and I don't want them to be Schwarzschild. I want them to be curved. I want them spinning. All right. So for that, we need extrinsic curvature. Where is it? Non-zero. Okay. So we go to the next level, and this is what most people use for numerical relativity. It's called Bowen-York data, or Bowen-York puncture data. So now, we still have asymptotically flat. We still have trace equals 0. We still have this one equals 0. We have still no matter. But k is non-zero. Then we have this equation to solve. Doesn't look very nice, but there's a analytic solution which has been found by these 2 people. And this analytic solution has 2 free vectors, S and P. And it turns out these 2 free vectors are exactly the total momentum and the angular momentum or spin. Exactly the free parameters that we want to have, they appear in this general solution. Okay? And because it's a linear equation, you make a superposition. And there's, let's say you have 5 of these punctures with 5 values of momentum and spin. And a total momentum is the sum of those, and a total spin is the sum of those. Okay? Very nice. Right. Small problem is that now you have a nonlinear Hamiltonian constraint, but we know how to solve these kind of equations. So essentially we're all set. This is kind of a regular term. So basically if the Brill-Lindquist data, they blew up like 1 over r, these are also going to blow up at 1 over r. So roughly they look the same as before. They have these infinities inside, which is a bit deformed. Okay? And so now I take 2 of these, and I get 2 spinning black holes moving with momenta p. All right? So I'm all set. I'm all set for numerical relativity. All right, I think I can go, there's some comments about how to solve them in practice. I don't think we have to go into those. There's a number of technical things that come in, very sophisticated coordinate system. But if you work in numerical relativity, you want to set up black hole initial data, you can, for example, go to this Einstein toolkit code. There's a module which is called 2 punctures, and you can use it to solve. I have a Mathematica code. If something is interesting, I can give you a Mathematica code which also solves these equations. Otherwise, let's not dwell on the technicalities. Let's talk about some other thing, which is junk radiation. So, as I said before, in general, so curved black holes or moving black holes, they're not conformally flat. They're like, they have some extra gravitational wave content, which is like undesired. Okay, some unphysical waves which are floating around. We don't want those. So, for example, here this is from some old, very old of our papers. This is some gravitational wave output from 2 black holes, where they're just doing this blop, colliding. And so you see, so this is with different spins, like 0 spin is black, and then the spin goes higher. And so the larger the spin, the more of this extra gravitational wave content you have in the beginning, which is not physics. You want to get rid of that. Okay? And so there's a way of doing this, which essentially is due to Sascha, which basically just take care of black holes. So the right solution, you deform them in some way, so that makes it easy to superpose 2 of them, and then you essentially solve the same equations as before. But the details are quite complicated. You may want to use this other variant of this conformal thing sandwich, but these are all technical details. One of the most important physical details is that the Bowen-York construction doesn't allow you to get spins larger than this. Just there's no solution. So if you want to have really large spins, then you have to do this kind of construction. And then also, what makes the evolution hard is what Rodrigo told you yesterday, that if the spin is higher, the black hole is smaller. Okay? So basically you need a lot more resolution, which is always expensive. All right. So this shows you from some other paper from the RT group. This shows you two evolutions, one with conformally flat data. You see a lot of this extra junk radiation in blue. And then if you did a method like this, there's a lot less of this. This is gone because all this unphysical radiation content has been killed out. Okay. Now, let me just check how much I have. But I have this. All right, I see. Now there's another important technical element that you have. So now you have a recipe to solve initial data. If I say I have these momenta and these spins, I have a recipe how to solve this. Okay. So how do I do it in practice? I say, well, what evolution do you want to do? And you say, I want two black holes at this separation, and one is supposed to have this spin, and one has to be this other spin, and we want them in orbit. But in order to get, for example, a circular orbit, how do I have to choose the momenta? All right, so that's the missing ingredient. If I choose bad momenta, they're just too large, you're gonna just fly away. Okay, I can simplify my problem to do what Jan has talked about. So I have my momentum, which is P1 plus P2, and now I use center of mass coordinates, so that P is 0 and P1 is minus P2, so that half the problem. But still I have to find this, my P1. All right? How do I get it? Well, for example, I could say that's sufficiently far away. I guess my momenta from the post-Newtonian solution. That would be a smart idea to do. But the post-Newtonian isn't that accurate. So what I will get now is, I start here, I use my post-Newtonian momenta, and then my separation as a function of time is kind of wiggly, because there's still some eccentricity. They are not circular, they're eccentric. All right? So now I have to find some better ways of doing that. And there's a long series of all kinds of papers about this. We have done the last one. I would claim it's the simplest method and the most accurate. So you want to set up non-eccentric initial data, or small eccentric initial data, or even eccentric initial data. Read this. You will find it very, very technical, and you don't want to read all the papers. And then you send me an email and say, can you send me the mathematical code that gives me the momenta? And I will say yes. Okay. So then let's not look at these things, and let's not talk about the phases of inspiral, because we have discussed this also. And let's just spend the last 3 minutes to say something about quasi-normal modes, which we have discussed, I think, on Monday. But let's say a few more things. So quasi-normal modes, we said, were if a system loses energy, you don't have normal modes, but you have like a damped oscillator, then they're called quasi-normal modes. You write your signal like this, that is frequencies that you can compute analytically if you know what the spin of the black hole is. However, so computing this is actually pretty complicated. It's well known, but it's somewhat complicated. So if you need to know what these frequencies are for a given spinning black hole, practical instructions are the two things that I think are very, very useful to know, or three things. First, you can go to this website of Emanuele Berti. You download all the data, like data. You can also download the code to produce the data, so that if you need more data points, you produce them with the code. Then you want to know roughly what's roughly the frequency or period. And so the number that I always remember is if for Schwarzschild and a dominant quadrupole is about 17M, or 16.7 or so. That's a useful number to remember. I can remember this number. So this gives you roughly what's the frequency of this ring down for Schwarzschild, which is good to remember. If you need more, then this is the picture for the two-to mode, what it roughly looks like, how these frequencies look like. Don't ignore the red curve. So the frequency for the oscillating frequency is this. You see it's getting much larger for, so this is the magnitude of the spin of the black hole, and now you can have black holes where we have waves going one way in the sense of the rotation, or in the other way. So in the sense of the rotation, the frequency goes up, go the other way, goes down, and then this is the damping factor. So you see if you have very highly spinning black holes and you go in the sense of rotation, there's not much development, but for very highly spinning ones, the damping decreases a lot. And I think that's all. Yeah. The plot is not symmetric because the physics here and here is completely different. So essentially the physics. Let's fix the orbital motion, so the black hole goes around this way, and so now for example, the spin of the central black hole, it can point up, which is this part, or it can point down. In one way, you're exciting waves which go with the rotation, and in the other way, you excite waves which go against the rotation. And so for Schwarzschild, these are the same, but otherwise they're not. They really have different physics. They're more damped or less damped. Okay? All right, so the timing I screwed up completely because I didn't talk about this, but in fact, this is just a few slides, so I'll talk about this tomorrow. Any questions? Coffee time. Any 1, 2, 3? Any question? Yeah.
In the slides when you show the expansion,
yeah.
you say that you will consider the 3D manifold, but this 3D manifold is Riemannian or
Riemann, the 3-dimensional constant time, we take it as Riemannian. Yeah. So like where we search for the horizon, for example, this is the t equals constant hypersurface, which now we take it as Riemannian. For the Cauchy problem, take it as Riemannian. All right. Coffee time.